Welcome back everyone. In this section we will learn about crown ethers and sulfides. So let's begin with crown ethers. These are cyclic polyether compounds which are derived from either ethylene glycol or substituted ethylene glycol. As we know that ethylene glycol molecule has two carbon chain and it is a diol. The structure of ethylene glycol is shown here. The crown ethers, which are derived from ethylene glycol, can be considered as a polymer of ethylene glycol. For example, the crown ether shown here is a hexamer of ethylene glycol. Crown ethers were discovered in early 1960s by Charles Pedersen, and he received a Nobel Prize for his discovery. These kind of compounds are known as crown ethers because first of all they do have ether functional group and their most stable configuration looks like a crown, which is shown here. So hence the name crown ether. These ethers are named by the system devised by Pedersen. According to his system, the parent name crown is used to describe crown ether, and the parent name crown is preceded by a number which describes the size of the ring. So in this case, the size of the ring is 18. So if we count, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. So the size of this ring is 18, so that number is preceded by the parent name crown, and the end name, which is 6 in this case, represents the number of oxygen atoms. So in this case we have 6 oxygen atoms, hence the name is 18 crown 6. The most significant structural feature of crown ethers is that the diameter of the cavity created by the interior oxygen atoms is comparable to the diameter of alkali metals. For example, the diameter of cavity of 18 crown 6 crown ether is comparable to the size or the diameter of potassium ion. So as a result, when a potassium ion is inserted into the cavity of 18 crown 6, the unshared electron pairs of 6 electron of crown ether are close enough to the potassium ion to provide very effective solvation of potassium ion. So what will happen in this case is that if a potassium ion is inserted inside this cavity, so potassium ion will form ion dipole interactions with all the oxygen atoms, which will create an effective solvation of potassium ion inside the cavity. So the interaction is pretty strong and the ion will stay inside the cavity. So hence the interior of the crown ether, because of the presence of polar oxygen atoms, so interior of crown ether is quite polar, but the exterior of crown ether contains only the CH2 groups. So hence the exterior is non-polar. Now because alkali metal ion is stable in the inside cavity, and the entire crown ether can be dissolved in a non-polar solvent, so this is a really good vehicle to dissolve polar ions such as potassium into non-polar solvents. So any polar ion which fits uh, the interior cavity of crown ether can be dissolved in non-polar solvent with the help of these crown ethers. So this ability of crown ethers to dissolve polar ions into non-polar solvent is quite useful. For example, potassium permanganate does not dissolve in benzene. However, if 18 crown 6 is added to benzene, the solution takes on the purple color characteristic of permanganate ion. So what happens is that permanganate ion goes inside the cavity of crown ether, and then the entire crown ether dissolves in benzene, and hence doing this will allow the permanganate ion to dissolve in benzene. So we know that permanganate, such as potassium permanganate, is one of the strong oxidizing agent. But the problem with permanganate ion is that it only dissolves in polar solvents such as water. But with the help of crown ethers, now we can dissolve permanganate ion in non-polar solvents such as benzene, and it can conduct oxidation of substances which are non-polar. So with the help of crown ethers, reactions such as oxidation by permanganate can also be carried out in water insoluble substances. Crown ethers have also proven valuable in nucleophilic displacement reactions. The cations of potassium salts such as potassium cyanide are very tightly bound within the solvation cavity of 18 crown 6 molecules. The anions, however, are only weakly solvated, and hence the anions, which are the nucleophiles, can conduct the nucleophilic substitution reaction more effectively. So therefore we can say that crown ethers are particularly useful in uh, conducting reactions which normally would not be possible in a particular choice of solvent. The final topic of this chapter is thioethers. Thioethers are also known as sulfides. These compounds are sulfur analog of an ether. In these compounds, we have a sulfur atom covalently bonded to carbon atoms which are part of a long alkyl chains. To write the IUPAC name of thioethers, we select the longest carbon chain as parent, and we name the sulfur containing substituent as an alkyl sulfanyl group. For example, if we have this thioether, in this case the longest chain is this one, or 3 carbon, so this would be a propane, and then the sulfur atom along with the smaller alkyl group will be considered as a substituent, and the name of this substituent is alkyl sulfanyl. So in this case it will be methyl sulfanyl. So therefore the complete name will be methyl sulfanyl propane. Examples of a couple of more thioethers are given here. In this case, the longest chain is ethane, and the substituent is also ethyl group. So the name IUPAC name is ethyl sulfanyl ethane, and in this case, our longest chain is propane, and the substituent is attached to number 2 carbon, and the name of this substituent is ethyl sulfanyl, so therefore the name is 2-ethyl sulfanyl propane. To write the common name of these ethers, we list the alkyl group bonded to sulfur and then followed by the word sulfide. For example, in this case, it is diethyl sulfide, and in this case, it is ethyl isopropyl sulfide. The alkyl groups are named alphabetically, so therefore, in the third example here, the common name will be methyl propyl sulfide. A disulfide is a class of organic compounds which contain a sulfur atom which is covalently bonded to another sulfur atom, and they are surrounded by two alkyl chains. The IUPAC name of disulfides are similar to sulfides. The only difference is that the subsequent group RSS is termed as alkyl disulfanyl. Rest of the rules are exactly the same. Again, we look for the longest chain and we consider the small alkyl group with the disulfide group as alkyl disulfanyl substituent. For example, if we have a methyl group on one side of the disulfide bond or group, and on the other side if we have propyl or ethyl group, let's go with ethyl, then our longest chain is the ethyl, not ethyl, in this case is ethane, and our substituent group will be the rest of molecules. So this is our substituent, and name of this substituent is methyl disulfanyl. So the complete name is methyl disulfanyl ethane. The common name is also similar to sulfides. Again, in this case, we list the ethyl groups in front, and the alkyl name of the alkyl groups are followed by the word disulfide. So in this case, the common name would be ethyl methyl disulfide. The alkyl groups are listed alphabetically. That's why ethyl is in the front and methyl comes after. Symmetrical alkyls can be prepared by reaction of alkyl halide or 2 moles of alkyl halide with sodium sulfide. Symmetrical sulfides are those in which the alkyl group on either side of the sulfur atom is same. For example, if we react bromoethane, 2 moles of bromoethane with sodium sulfide, we will get diethyl sulfide plus 2 moles of NaBr. A similar reaction can also be used to prepare 5 or 6 membered cyclic sulfides. An example of a preparation of 5 membered sulfur containing cyclic sulfide is shown here. Unsymmetrical sulfides can be prepared from thiols. In this reaction, first a thiol is reacted with a strong base such as sodium hydroxide to convert the thiol into sodium salt of the thiol. The name of these sodium salts are sodium alkyl thiolate. For example, in this case, our carbon chain is 1, 2, 3, and 4. So it's butane thiol. So the name of this sodium salt is sodium. It is 1-butane thiol. So the name is sodium 1-butane thiolate. So once we prepare the thiolate, sodium salt of thiolate, then this sodium salt of thiolate is used as a nucleophile, and it is reacted with any alkyl halide of your choice. For example, if I use a methyl iodide, in this case the thiolate will perform a SN2 type of reaction, and we will get an asymmetrical sulfide, in which one side is 4 carbon, the other side is methyl. So the name of this sulfide is butyl methyl sulfide, and of course this is a common name. You can write the IUPAC name if you like, and plus sodium iodide. So by choosing the appropriate thiol and appropriate alkyl halide, we can prepare any asymmetrical sulfide. One of the important property of sulfides is that they can be used as reducing agents. The reason why they act as reducing agents is that because they themselves can be oxidized into higher oxidation states. So when sulfides are oxidized, they convert into sulfoxides or sulfones. Many common oxidizing agents can be used to oxidize sulfides. For example, hydrogen peroxide at room temperature can convert sulfides into sulfoxides. Other oxidizing agents such as sodium periodate can also brought about the same oxidation reaction, and sodium periodate can further oxidize sulfoxide into sulfone. So in sulfone, sulfur is bonded to 2 oxygen atoms, and in sulfoxide it has only 1 oxygen atom bonded to sulfur atom. The oxidation of dimethyl sulfide by gaseous oxygen is a commercially important reaction. This reaction is used in the industrial production of DMSO, and the DMSO is used as a common proteic solvent in many organic reactions. With that, we conclude chapter number 11. In this chapter, we learn about ethers, epoxides, crown ethers, and sulfides. Thank you for watching the video. If you have any question, please let me know. Have a wonderful rest of the day. Bye-bye.